What's the second example? 5, 6, 7, 8, 9?
I think 9 will. 8 and 9, 8 and 9 go together. 8 is the ionic reactions or addition reactions of alkenes, and 9 is ionic additions of alkynes. And we'll see that they're very, very similar. So if you know one, you know the other. All right, chapter 7 is going to review a lot of things we said about alkenes way back when we did our first introduction to functional groups. We will then move into the notion of degrees of unsaturation. And then finally, we will do alkene nomenclature. We talked about alkenes. This is ethene, carbon-carbon double bond. Remember, these are both sp squared carbons. Because of that, they are trigonogeometry. The molecule is nice and planar. Here's our carbon-carbon bond. Again, let it get around. You can see it's nice and planar. Again, 120-degree bond angles. We form this by taking 1s and 2 of our p orbitals. We combine these to make an sp squared hybrid. The hybrid forms our sigma network. That's the actual carbon-carbon, carbon-hydrogen bonds. We also have left over 2 of our p orbitals, 1 on each carbon. When we put these in, they're going to go here, 1 on each carbon, and they're going to line up like this. We said that when orbitals align with each other, when they are absolutely straight up and down, we have the potential for overlap. Overlap means we can share electrons between them. When we do that, we form this pi system, simply formed by the sharing of these electrons in the adjacent p orbitals. We cut this open. Again, this is our sigma bond. These are all of our sigma bonds. They're from our sp squared. And our pi bonds are constructed from our leftover p orbitals. Now the pi bonds, like we saw in the last chapter, are important because this is where the electron density is going to be. This is where the reactions are going to occur. When we draw a double bond, remember this is a shortcut. We always remember one of these is a real sigma bond, and the other one is simply this pi bond. Any questions? Now we said that one of the things about alkenes was that because we formed our second bond, our pi bond, by overlap of these orbitals, we were not allowed to rotate this sigma bond. If we did, we would wind up with this structure. And in this guy, our overlap between the adjacent p orbitals is 0. When we go from this orientation, which is an energy minimum, to this orientation, which would be an energy maximum, we have to put a lot of energy in the system to do it. Because of that, we do not have free rotation around a carbon-carbon double bond. Now the result of that was that we could have stereoisomers. This was the first type of stereoisomer we looked at. We basically said that because we can't rotate around this bond, that these were different compounds. When we have a double bond with our substituents attached on opposite sides of our double bond here, we call that trans. And when they were attached on the same side of our double bond, we call that cis. Now in those days, that was fine. We'll see that this doesn't quite work for more complex compounds, but we have a solution. Before we go and talk about stereochemistry and nomenclature and whatever, let's just go back and let's address the functional groups that we've talked about so far. We said that alkanes were going to have the general formula CnH2n plus 2. N is the number of carbons. So if we have 10 carbons, we would have 22 hydrogens. That's a simple alkane. We saw that if we made a cycloalkane, that our general formula changed. For a 6-member ring, we have C6H12. That's CnH2n. Same thing if we have a 5-member ring, C5H10, CnH2n. Well, alkenes are the same as cycloalkanes. This just represents a generic alkene, C6H12. Again, N is 6, H is 12. So cycloalkanes and alkenes are both CnH2n. Now the fact that we have 2 missing hydrogens in between alkanes and cycloalkanes and whatever is actually a useful tool when we're trying to figure out a structure. We can refer to the missing hydrogens as a degree of unsaturation. A single degree of unsaturation means that your compound either has a ring or a double bond. And for every ring, you have one more degree of unsaturation. For every double bond, you have another degree of unsaturation. Like I say, this is useful if you're trying to figure out a structure based on analytical data. Now, next semester, we're going to do spectroscopy, and we're going to be doing unknowns like mad, looking at spectra, looking at analytical data, and figuring out what these compounds are. This is one of the tools that we're going to use. Look at these compounds. Tell me how many degrees of unsaturation we have in each. The hard way is to look at the compound, add up our carbons, 1, 2, 3, 4, 5, 6, and then count the hydrogens. There are 12 of them. Based on our formula, we're missing 2 hydrogens for a simple alkane, therefore we would have 1 degree of unsaturation. The simple way to do it is just to look at the compound and say, well, I've got 1 double bond, I will have 1 degree of unsaturation. That's simpler, don't even have to count. Our next guy, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons and 16 hydrogens. If this was a simple alkane, it would have 22 hydrogens. So we're missing 6 or 3 degrees of unsaturation. You could also just look at it and say, I have 1 ring and 2 double bonds, 3 degrees of unsaturation.
Can you go back to the slide?
Hmm?
Can you go back to
Go back to this one.
yeah, just continue to go back to the slide.
Go back, previous slide. Okay. This would have 14 if it was a simple C12 alkane, or C6H, C6 alkane. We're missing 2 hydrogens, 1 degree of unsaturation. All right, look at these 2. Now, at this point in your life, doing the first one, you might be better off just to count carbons and hydrogens. We have 6 carbons, 7 carbons, don't we? CH2, 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 and both of these are CHs. That's C7H12. If we had a C7 alkanes, we would have 16 hydrogens. Therefore, this has 2 degrees of unsaturation. Yeah.
Sorry, how are you doing that 16?
Oh my, where does 16 come from?
Yeah.
If we had 7 carbons, N would be 7. 2N is 14, plus 2 more.
Oh, so N is the number of carbons.
We can also just look at this and say, well, we have 2 rings, so we obviously have 2 DUs. But you might not be able to look at this and say, there are 2 rings. Not yet, but you will in a minute. Because there's a rule. This is a polycyclic compound. When you're dealing with a polycyclic compound, and you want to know how many rings you have, the procedure is actually simple. What you do is you start somewhere, anywhere, and you go around and you trace out a ring. Then you look at what's left, start somewhere else, trace out another ring, starting somewhere, ending somewhere. You're not allowed to retrace any path, but you can connect atoms on the 2 paths. So what this means is, we start off with this. I could just say, all right, I'm going to start here, and make that a ring. Okay, makes sense? Now, I have to start somewhere else. Like I could start here and trace the second ring this way, connecting the 2 paths, but not retracing anything. 2 rings, 2 degrees of unsaturation. This one, methyl cyclohexane, this is trivial, isn't it? We have 7 carbons. We have 14 hydrogens. We should have 16. Therefore, this is 1 degree of unsaturation. You would look at this and say, 1 ring, 1 du. Now we know that organic compounds don't just contain carbon and hydrogen. If you happen to have a halogen, you would just convert it in your mind to a hydrogen and go with it, because it's the same thing. Oxygen. What you do with oxygen is you simply ignore it. Just ignore it. Pretend it's not there. So, for this compound, we have 1, 2, 3, 4, 5 carbons. We have 10 hydrogens and an oxygen. But we'll just say C5H10O is the moral equivalent of C5H10. If we add 5 carbons, we would expect 12 hydrogens. Therefore, we have 1 degree of unsaturation. Just ignore the oxygen altogether. 1 ring, 1 du.
So for that one, like if you were actually gonna map it out completely, I know there's only 5 carbons, but like where are the hydrogens placed, I guess?
Well, each of these is a CH2, isn't it?
So there's no hydrogens on the oxygen?
Nope,
And
nope,
that's,
nope. Oxygen forms 2 bonds.
and then it has 2
2 unshared.
unshared.
All right, here we have an alcohol. Again, we're going to do our formula and just ignore the oxygen. This is also C5H10O. Ignore the fact that we have an oxygen. We have 1 du. 1 ring, 1 du. The rule for nitrogen is a little different. Again, we're going to ignore the nitrogen. But because nitrogen comes with a hydrogen attached to it, we have to ignore the hydrogen too. So if you have a nitrogen in your compound, you ignore the nitrogen and 1 hydrogen. 1 hydrogen for every nitrogen, you just drop out. So this thing would be C5, H10, 11, and a nitrogen. We'll drop out the nitrogen, 1 hydrogen, and say this is equivalent to C5H10.
It's only with nitrogen, right?
Yep, that's for nitrogen. Once again, 1 ring, 1 du. It doesn't matter if our nitrogen in the compound has 1 hydrogen or 2. We're going to treat it the same way. We're going to get rid of the nitrogen and 1 hydrogen. Again, we can call this equivalent to C5H10 or 1 du.
So what are you doing with the whole, like, it should have 12? And what's the point of
I'm sorry?
like, what's the point of, like, figuring out, like, how many hydrogens it should have? Like,
Well, how many degrees of unsaturation? How does this work into an analytical problem? Well, part of the analytical data you'll be given next semester is going to be a molecular formula. You can take that molecular formula and immediately, using this, say, well, I have 3 degrees of unsaturation. So I'm looking for 2 rings and a double bond, 3 double bonds, whatever. So that's the way it's useful in analytical determination. It's a very simple exercise, actually. Yeah.
So if you got something that said C5H10 with 1 degree unsaturated, you would know that it should look like that.
Well, you would know that it would have either one ring or one double bond. That's all you would know. But if you're trying to figure out what it is, then this gives you an idea of what to look for. Let's say that we had just done this particular steroid aldehyde. How many degrees of unsaturation would we have here? This one was actually on the exam. All right, the long way. C25H40O. It's a long way, because that's a long way to count. We know we're just going to ignore the oxygen, aren't we? So if we had 25 carbons, we should have 52 hydrogens. Therefore, we are missing 12 hydrogens or 6 degrees of unsaturation. Now that's the long way. What's the easy way? We have 1, 2, 3, 4 rings, right? We have 1 double bond. We have 2 double bonds. We have 6 degrees of unsaturation. See how simple this is? On last year's exam, there were 2 questions. There was this one, and of course, there was this one. This is cubane. It's a real molecule. Very high energy, lots of ring strain. Actually used as a rocket fuel. How many degrees of unsaturation? 6. Again, because you're beginners, you would probably be best just to say, well, I have 8 carbons, right? How many hydrogens are there on every carbon? 1. C8H8. If we had 8 carbons in a simple alkane, we would have 18 hydrogens. We are missing 10. Therefore, this has 5 degrees of unsaturation. Now remember I said we could count the rings. That's the fun way to do it. We'll start somewhere and we'll make a ring. That'll work. Now we're going to start somewhere on one of these carbons and make another ring. And do the same thing down here. Finally, we have 2 bridges we can construct, this one and this one. Therefore, we have 1, 2, 3, 4, 5 rings in our compound.
What did you mean by bridges? What do you mean by bridges for the last 2?
Well, on our last 2, we have a bond here we haven't counted, right? We're allowed to go from any existing ring to any other. Therefore, we can just start up here, go down, start here, and go up and down, like that.
I guess I just didn't think it would be a ring, it's just.
Yeah. Even though it's no carbons in it, it still counts as a connection. Any questions on degrees of unsaturation? We'll use it a lot next semester. Right now, there'll just be a couple very simple questions on the exam. Every time we do a new functional group, first thing we're going to do is name it. Did that with alkanes, now it's the alkene's turn. Number 1, we're going to look at the longest continuous chain. Only difference is it must contain the double bond. The longest chain containing the double bond. We're going to take our parent for the number of carbons and add E and E to show it's an alkene. This is going to be our longest chain containing the double bond. That's simple. Number 2. 5 carbons, this is a pentene. Number 2, we're going to number it. But we're going to number it in such a way that we're going to give our double bond the lowest possible number. We're going to ignore all the other substituents and simply say we want our double bond to have the lowest possible number. So that means we're going to start numbering here. 1, 2, 3, 4, 5. So this isn't just a pentene, this is a 1-pentene. Now we go and we look and see what else is attached. If we had more than one double bond, we would call it diene, triene. In this case, we only have an ethyl group here attached to carbon 2, so we would stick it in 2-ethyl 1-pentene. So the only thing you have to remember is, make sure your parent chain contains a double bond. Number it so the double bond gets the lowest number. Everyone see this? All right, if we look at this guy, our longest chain is going to be 1, 2, 3, 4, 5, 6, 7. Correct? We're going to start numbering here. So our first alkene carbon is carbon 3. If we started numbering here, we would be at 1, 2, 3, 4. Therefore, this is carbon 1. We have 2 ethyl groups here at carbon 6. So we're dealing with a 3-heptene with 2 methyls at carbon 6. See how simple that is? Now we also learned how to name cycloalkanes. If we have a cycloalkene, the rule is that we're going to start at one of our double bond carbons. And we're going to proceed numbering through that carbon. Now with this one it doesn't matter, but if we define this as carbon 1, then this must be carbon 2. Now with this particular compound, we have a 6-membered ring, and it's cyclic, so it's a cyclohex, isn't it? It has 2 double bonds, so it's going to be a diene. And those double bonds are located at carbons 1 and 4. It's a cyclohexadiene. Carbon atoms are the double bonds are located at carbons 1 and 4. 1,4 cyclohexadiene. All one word. Let's say we had this guy. If we didn't have the double bond in there, it would scream at us that this should be carbon 1, right? But we must start numbering at the alkene and proceed through it. Now, we could do that calling this 1, that 2, or this 1 and that 2. If we started this way, we would have 1, 3, right? 6, 6. If we went this way, we would have 1, 3, 3, 6. 2 3s is better than only 1. Therefore, we're going to number it clockwise, 3, 3, 6, as opposed to 3, 6, 6.
Why couldn't you start numbering 1 where 2 is?
Well, if we
Like a
did,
1, 2,
then this
2.
would have to be 2. That's 3. That's 3, 6, 6.
No,
This
why
one.
couldn't you do 1, 2, 2, 3?
Because the rule says you must go through the double bond.
Oh.
Carbons 1 and 2 have to be the double bond carbons. Therefore, this is a cyclohexene. We have methyl groups in carbons 3 and 6, and we have 3 of them.
So would you get it wrong if you threw in the 1? So you said 3, 3, 6 trimethyl 1 cyclohexane?
You don't have to put the 1, because by definition, 1 and 2 have to be your alkene carbons. You
So-
only need to put in a number if you have more than one double bond. In a ring, 1 and 2 must be your alkene carbons. So we know that either this or this is going to be 1 and 2, right? We know that. Simply have to decide, are we going to go clockwise or counterclockwise? If we go clockwise, we would have 1, 4, 6, 6. If we went this way, we would have 1, 2, 3, 4, 5, 5, 7. 4, 6, 6 is better than 5, 5, 7. This is a cyclooctene, isn't it? We know where carbons 1 and 2 have to be, but we have methyl groups in 4, 6, and 6. Now here we're going to have to include numbers because we have more than one double bond. We would probably love to put this as carbon 1. So we would have a 1-methyl. But remember, we always want to give our double bonds the lowest number. So if we made this carbon 1, that would have to be 2, 3, 4, 5. It'd be a 1,5 diene, wouldn't it? Instead, we want our double bonds to have the lowest number. Therefore, this is going to be 1, so we can have a 1, 3 for our double bonds. Double bonds take priority. We would call this a cyclohexadiene. We have a methyl group in carbon 2. Remember, this is not 1-methyl, 1,5, because we want 1,3 for our double bonds, not 1,5. All right, there's one other aspect of nomenclature we have to address. Remember we said we can have cis and trans isomers? Can't have free rotation, therefore we can have cis and trans. If they're on opposite side, they're trans, same side, they're cis. That's really simple, isn't it? So, if I said, name this guy, you would look and say, I have 4 carbons in a row, that's a bute. It has a double bond, so it's a butene. And the double bond is in carbon 2, so it's a 2-butene. And the stereochemistry is trans. Trivial, we can all do that. Let's make sure we can all do that. All right, so you can do that. Name this one. Well, are we going to say this is cis or trans? We're going to say, well, we'll do it alphabetically? No. We need to figure out a way to name compounds that are more complicated than something like this. Fortunately, in Chapter 5, we learned a set of rules, didn't we? They are called the Kahn, Ingold, Prelog rules. And we're going to use those same rules. So you learn them once, you get to use them twice. You're going to use the same rules for stereochemistry on an alkene. I remember the first thing we did was we looked at what was attached, and we looked at the atomic numbers. That was our highest priority, was atomic number. Then we said, whoops. Then we said, hang on. Then we did clockwise, counterclockwise. For an alkene, instead, we're going to say, are the highest priority groups on the same side or on opposite sides? If they're on the same side, we'll say this is Z. If they're on opposite sides, we will say it's E. Z stands for zusammen. Zusammen is German for same side. E stands for Antagon, which is opposite. We learned that if we have a tie, we just keep going on our chain till we hit a tiebreaker, just like we did for R and S. Same side is Z, opposite side is E. Let's apply it. Look at each of our alkene carbons, do atomic numbers for what's attached. Let's see, 1, 6, 6, and 35. On this carbon, whose highest priority? The carbon. On this one, highest priority is the bromine. These are on the same side. This is Z stereochemistry.
On the last slide, you had it as CLBR. So is this a different?
It's a different molecule, and we'll go back. We'll do that one too. Just like we did for R and S, we're going to take our E and Z, put it in parentheses in front of our name. 2-bromo, 2-butene, and our stereochemistry is Z. Here we are. This is the one we started with. Our atomic numbers are going to be 1, 6, 35, and 17. On this carbon, this is our highest priority. On this one, the bromine is the highest priority. Same side. This is Z stereochemistry. It's a propene. In carbon 1, we're going to have a bromine and a chlorine. In carbon 2, well, we have nothing. And our stereochemistry is Z. Just like before, if we have a tie, we keep going till we get a tiebreaker. In this compound, we have carbon, carbon, carbon. Those are all 6s, aren't they? So we look and we say, what is this carbon attached to? 3 hydrogens. What is this carbon attached to? 2 carbons and a hydrogen. This guy wins. We have E stereochemistry. We would start numbering this guy here, right, to give our double bonds the lowest number. So this would be a 1, 2, 3, 4, 5. It's going to be a pentadiene, a 1, 3 pentadiene with a methyl in carbon 3. 1, 3 pentadiene, carbon and methyl, or methyl and carbon 3. And E stereochemistry.
Can you go one slide back?
Hmm?
Explain that
Yeah.
one more time, please.
Well, explain which one.
Um,
Let's explain it all. That's okay. Here we have a tie. This one is obviously the winner. Haven't we seen that? Here we have a tie. Now the rules, just like the rules we use for E and for R and S, right? What we do is we say, okay, we've tied on this carbon. What is this carbon attached to? 3 hydrogens. Double bond counts twice here. So this carbon is attached to this carbon twice and to a hydrogen. Therefore, this is higher priority than this guy. Exactly the same thing we did with R and S. Learn it once, use it twice. One more example. You do this one and I'll hush. On our first alkene carbon here, this one is going to be the winner. On this alkene carbon, we have carbons attached on both sides. So you look and say, okay, this carbon is attached to what? 2 hydrogens and an oxygen. This is attached to a hydrogen, which we don't show, and 2 carbons. So which is the highest priority group? Remember, atomic number is the first determinant. Oxygen is a higher atomic number than carbon. Therefore, this is Z stereochemistry. Same side. All right, let's do a couple exam problems.
Can you go back to that name? Because-
Oh, the name?
Yeah, thank you.
Here I call this group isopropyl. Remember, you could do it methyl ethyl. We don't know how to name alcohols yet. That's why I skipped over the name. But to show this is an alcohol, we would call this a butene 1-ol. That has a double bond and an alcohol, butene-ol. And an isopropyl group here in carbon 2. But we don't know how to do that yet. But we do know how to do these guys. So quickly, jot down IUPAC names for these simple alkenes. If you're not printing the lecture slide many ways, you really should. It saves you so much time, makes it so much easier. This is a cyclohexene, isn't it? We know that carbons 1 and 2 are going to be these guys. We want to come up with the lowest number sequence. So probably we want to let this be carbon 1, don't we? That's going to give us a 1-methyl. Our double bond is here between 1 and 2. And we also have a methyl here in carbon 3. This is going to be a 1,3-dimethyl cyclohexene. Do we have to indicate cis and trans? This is where, on the exam, people got it wrong. No, we don't. Because remember, this is planar here. We draw it as a chair, but that's just because we know how to draw chairs and we're trying to show off. Okay? This is actually planar. So it's splitting the plane between these two. There is no cis and trans. Our next one, simple, just long. We have a double bond here. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So it's going to be an octene, isn't it? We want to give our double bond the lowest number. So we want to start numbering here. We have a 3-octene with methyl groups in carbons 4 and 7. No, I'm sorry. Methyl group in carbon 4, a chlorine in carbon 7. Putting them together. Oh, we also need to show stereochemistry. Again, these would both be carbons. But this has 3 hydrogens. This is attached to a carbon. Therefore, this is going to be the moral equivalent of cis, which is Z. 7-chloro-4-methyl, 3-octene. Yeah.
So when do we have to put in the stereochemistry? Like, is that-
Whenever there really is stereochemistry.
Okay,
Cis and trans would be different compounds.
okay. So, but like, so in the first one,
If
right?
it doesn't matter, it doesn't matter.
Okay.
But if it does, it does. That sounds stupid, but it's true.
Can you go back, please?
Z, 7-chloro-4-methyl, 3-octene. We have a cyclohexene, don't we? We know that our double bonds are going to be carbons 1 and 2. We want to come up with our lowest number sequence. If we let this be carbon 1, then that would have to be 2. Our first substituent would be here in 3. If we let this be carbon 1, our first substituent would be in carbon 2. Did I just number this wrong? I guess I did. I think this is wrong. I think that should be 1, 2. Yeah, this should be 1. No, because maybe this is right, because this would be 1, and 1 would come before 2. So I guess my explanation was wrong. I'm sorry. I lost some credit. But if we let this be 1, our number is 1,556 with a 3-ethyl. Otherwise, it would be a 2, 3, 4, 4. And 1 is less than 2. This is correct.
Wait, isn't 4 less than 5?
But our first number here is 1. If we did it the other way, our first number would be 2. 1 is less than 2.
I understand that, but should you have a smaller amount of numbers?
Doesn't matter. It's only the lowest number at the first point of difference. All right, let me try again on this one. This is going to be a cyclooctadiene, isn't it? We know that we have to start at our double bond and number through it. We could let this be carbon 1, and that would be carbon 2. Doesn't matter if we go this way or this way, our double bonds are going to be carbons 1, 2, 3, 4, and 5. Carbons 1 and 5 for our double bond.
Don't we have to go clockwise though? Since that would be a 1.
So we would let this be carbon 1. Our diene is a 1,5 diene. 1-ethyl, 1,5 cyclooctadiene. Two more. For our first one, we're going to have to figure out if it's E or Z, right? Is this going to be E or Z? On this carbon, we have a methyl and a chlorine. Chlorine is going to win, isn't it? On this carbon, we have 2 carbons. This is 3 hydrogens. This is 2 hydrogens and a chlorine. So this guy is going to win. If we start numbering here, we will have a 1-chloro substituent. We have 3 carbons in our chain. Z, 1,3 dichloro, 2-methyl, 2-butene. 4 carbons in our chain, not 3. Yeah.
I have a question. Instead of having like the chlorine attached, what if it was just a CH3?
If it was a CH3, then it would make no difference because we have 2 of the same thing attached.
Okay.
And it would neither be E or Z. And our last one here, a cyclopropene. We know that we must have carbons 1 and 2 as our alkene carbon, right? If we let this be carbon 1, then our first substituent would be here. Therefore, this is a 1,3 dimethyl cyclopropene. No stereochemistry, because this is flat. Now, this name that we just assigned this, could we enhance that at all? Is this compound superimposable on its mirror image? This carbon attached to it, CH3, a hydrogen, an alkene with a methyl, an alkene with a hydrogen. 4 different things, aren't they? So we would actually, to do the full name, have to say that this was, the clock goes that way, that makes it R, right? So this is a 3R, 1,3-dimethyl cyclopropene. On the exam, I didn't make you do that, but just so that we know we can.
So it's 3R.
Just 3R in front. Any questions? And then we will have another period to go over it. As I mentioned, there is an awful lot of material in this chapter. But we will attempt to do it in a very organized way that hopefully will make it very, very simple for you. Hopefully. All right, addition of HBr. What we're doing is basically taking an alkene, reacting it with HBr. When we do this, we add the hydrogen to one carbon and the bromine to the other. It's a very simple addition reaction. On the slide here, it says rearrangement is often observed. Now, we haven't talked a lot about rearrangements yet. We'll address those more as we go forward in the course. But a rearrangement simply means that the connectivity of the particular compound changes. So if we have a more complex alkene here, quite often it would rearrange its carbon skeleton during this process. Rearrangements are often observed in reactions involving carbocation intermediates. The addition of HBr does in fact involve a carbocation. Remember that when we talked about the pi system for an alkene, we said that there was a rich electron cloud on both sides, above and below the plane of the double bond. See this in the electrostatic potential map. as a nice big red splotch. This is actually the point at which the reaction begins. Now, most people don't address this as part of the mechanism, but I do because I think it's important to understand exactly how the carbocations that can form do. This is our simple IMO diagram for our pi system. And again, as we saw in the electrostatic potential map, there is lots of electron density here. Functioning as a Lewis base, that's an electron donor, this pi system can accept a proton from HBr. So HBr acts as an acid, a Bronsted acid if you will. The pi system would function as a proton acceptor, that makes it a Bronsted base, or as an electron donor, making it a Lewis base. This is the intermediate that most people don't talk about, but it only makes sense to mention it because this is how the reaction must start. Once we make this very fleeting intermediate, very, very, very fleeting intermediate, this is going to rearrange to give us carbocations. There are two possible ways that this intermediate could rearrange. One would be to have the hydrogen slide down to this carbon. Other, the hydrogen would slide down to this carbon. If we slid down to this carbon, this would now be a CH2, CH3. We put the proton here. And that would leave this carbon with only 2 hydrogens and 3 bonds. That means it is positively charged. Its formal charge is +1. This is a carbocation, also called a carbonium ion in many places. If in fact the hydrogen slides down to this carbon, we get this carbocation. Now, the fact is that this reaction doesn't occur just randomly. That in fact, this pathway does not occur. That when we form protonated pi cloud, it always rearranges this way to give this carbocation.
So that goes to the methyl.
Hmm?
Is that also like that because of the methyl group?
Well, yes, it is actually. It is because of the difference in the carbons. This is a secondary carbon, and this is a primary. What we're talking about here is the difference in inherent stability of the ions. A secondary carbocation, we'll see in a minute, is more stable than a primary. So nature is going to go, this proton is going to slide to form the most stable intermediate. So when you do a simple ionic addition to an alkene like this, you are always going to do so to form the most stable intermediate. This is Markovnikov's rule. Now, as I mentioned, Markovnikov was a Russian chemist, and he was studying these things, and he observed, very empirically, addition of HBr to an alkene. The hydrogen with the greatest number of hydrogens will get the hydrogen. Now, this is restated as them that has gets, etc., etc. From here, this carbon has 2 hydrogens. Markovnikov said it will therefore get the hydrogen. This one has 1 hydrogen, and it won't.
I see 2 hydrogens in that one, but that one has 1 hydrogen that it's got the carbon. So that,
This guy?
yeah.
This is a primary carbon attached back to only 1 carbon.
Right.
This
That was
is
attached to 2
one
carbons.
that doesn't form. This one's attached to 2 carbons.
Right.
Now,
But you said hydrogens.
Right, well, that's what Markovnikov said.
Right.
So you look at the alkene with Markovnikov. You look and you say, 2 hydrogens here, 1 hydrogen here. This guy gets a hydrogen.
Right.
It's better, I think, to think about it in terms of carbocation stability. Carbon with the greatest number of hydrogens get the hydrogen, but overall, the most stable carbocation is always going to be formed. So what we need to do is to develop an understanding of carbocations and what makes them stable. A carbocation. Take a carbon, take off a bonding pair of electrons. We're left with a center with 3 bonds to it and a formal charge of +1. This is an sp squared carbon. Now it has a p orbital still left on this carbon, but it's empty. So this is trigonal geometry, just like anything else is sp squared. Has the same sp squared p orbital, but it is empty. This is what a carbocation is. The simple fact is, well, because it's sp squared, again, all these angles are 120. The simple fact is that there's a very reproducible ordering in stability. If you have a tertiary carbon, so a carbon bonded to 3 other carbons, that will form a fairly stable carbocation. Secondary will be less, primary will be less stable, and a methyl is very unstable. So when you do an addition to an alkene, you want to look and see what type of carbocation would be formed on each carbon. In this case, we had a secondary versus a primary. This is more stable. This is the one that's going to form. You can also see this if you look at the electrostatic potential mass. Remember, blue means positive charge. If we have a tertiary carbocation, you'll note that we have a little patch of blue, kind of like nice sky blue in the middle. Secondary, we have a bigger patch. Down here to a primary, this is very, very positive. The reason that this occurs is that alkyl groups in general, an alkyl group is basically any carbon that's attached out here. These things are electron donating inductively. That means that they can release electrons through this covalent bond to stabilize the positive center. The more groups you have around, the more electrons are released into the middle, and the more stable it is. Now we'll see that there are carbocations that are more stable than tertiary. Those are the ones that typically are stabilized by resonance. But we'll see those in a minute. Right now, the simple thing to look at is tertiary, secondary, primary, and methyl is very, very bad. Any questions? Yeah.
For the tertiary carbon, let's say one of those methyl groups was like, not a methyl, but like maybe like a COH or something. Would that be still
So you mean a
tertiary?
longer chain?
Or just like if you look like the top methyl group, what if it was a COH?
Well,
Would it still be a
then it
stable?
gets a little bit more difficult.
Okay.
It would still be a tertiary carbon, but if you had a hydroxyl group out here or something, hydroxyl group would be inductively electron withdrawing.
Right.
So
Okay.
it would get,
So
more.
it'd be less.
Yeah, it would. But right now, let's just settle on our very simple alkenes and their thing.
So you just mentioned longer chains, is that having to do with?
Longer chain
strength?
doesn't have much of an effect.
Okay.
It's mostly the carbon that's right next to the positive center. All right, let's look at this in terms of a reaction coordinate diagram. Again, we kind of did this last time. We're starting off here with our alkene and with HBr. Our products are over here. This is the bromo, 2-bromopropane. As these things begin to react, we go through a transition state. In this transition state, we're going to form this carbocation intermediate. Now actually in a pre-equilibrium, before the transition state, we're going to protonate the pi cloud. But at this level, most people don't address that. Just remember, there's a nice rationalization as to why it happens at all. So we go through a rate-limiting transition state, highest energy, and we form the carbocation intermediate. The next step in the reaction is going to be a fast step, because carbocations are very reactive species. What we have is bromide anion floating around in solution. We get that from HBr. Proton goes here, bromide's left over. Bromide is now our nucleophile. Remember, a nucleophile is looking for a positive center. There's one. Bromide attacks. We have a fast step now, so a small activation energy to give our final product. Slow step, also called the rate limiting step, gives us our intermediate. Fast step gives us our product. Any questions?
Wouldn't you want to number it as well?
Want to number it?
So it was like E and Z.
I'm
If
sorry?
it- E and Z, if it had like two bromide ions or two methyls.
We will see in chapter 8 that if we add something like bromine, Br2, to an alkene, we will get a trans 1,2-dibromide. And so, yes, E and Z would be in effect there. Not here. Let's look at this actually made it in about 98, but this 2000 movie with the addition of HBr to an alkene. Step one, we're going to simply protonate one of the carbons. Remember, initially we're going to protonate the pi cloud, then it rearranges. Step two, bromide is going to attack, and here's our product. HBr comes in, we donate a proton. We now have a carbocation. Now, because this is planar, bromide could attack from the top or the bottom with equal likelihood. In this case, we've shown attack from the top, and we simply get our alkyl bromide. So much fun, let's watch it again. Step one, we're going to protonate. We make our carbocation. We could attack from the top or the bottom. Attack from the top gives us our final product here. Any questions?
What allows it again for it to be able to go from the top or the bottom?
Because remember, the carbocation is sp squared, so it's planar. Because it's planar, pathway to the top and the bottom are the same. Yeah,
So it takes the hydrogen first.
right.
And then-
Think about the hydrogen going on first. In reality, it goes on the pi system first, then goes to the carbon. But as far as you need to know right now, it simply goes to the carbon. Markovnikov said the carbon with the most hydrogens, I say to form the most stable carbocation. All right, let's look at this. Very quickly, predict the initially formed carbocation. Actually, why don't you draw both of them? Choose the one that's going to be formed, and then draw the final product. Now, being very Markovnikov about this, this carbon has a hydrogen, this one does not. So Markovnikov would simply have us put the hydrogen here, and that would give us this intermediate. I would simply look at this and say the proton is added to give a tertiary carbocation. If we put the proton on this carbon, and let's refer to that as the anti-Markovnikov carbon, we would get this guy, which is a secondary carbocation.
That would happen.
We all know tertiary is better than secondary. Therefore, these are the two possible carbocations. The one that will be formed is this guy. Step 2, we're going to take and add bromide, Br minus, to the carbocation. And our product will be 1 bromo, 1 methyl cyclohexane.
So in that one, the hydrogen basically attacks the double bond, and it's either going to go across secondary or tertiary.
Right.
And it wants to go tertiary, and then it's just
It forms the most stable carbocation.
Alright, so I understand how it all forms, but I have a little bit of a trouble seeing the stereochemistry as the bromine kind of strain on the actual
The ring
snake.
itself?
Yeah, the ring itself, yeah.
Yeah, sure, of course it is.
With
It's
so
a
much
fairly
yeah.
unstable product.
Okay.
The bromine is bigger, it's going to want to be equatorial.
Right.
Methyl doesn't like to be axial,
So
so
like
it's
if
going
you
to
have
be
like the
distorted.
chair, if you have the chair formation and
Yeah.
everything, it's got to make it,
It's going to be a distorted chair.
okay.
A little bit of twist boat character.
So
But-
now I want to be in that setup
Right.
for a long time.
Now, because this has a plane of symmetry, we don't have any stereochemistry here, do we? This is not a chiral center. Same path going around both sides. This is not a chiral center. All right, let's take this guy. Go ahead and add HBr. And look at the carbocations that you would form. When you have a ring, a benzene ring, and next semester we'll understand why people often draw this with a circle in the middle instead of individual double bonds. But if you have a benzene ring, and you have a carbon attached to it, the carbon at this position right here is referred to as a benzyl carbon, B-E-N-Z-Y-L.
Which carbon?
Benzyl, one that's directly attached to the ring. So we could get two carbocations here. We could get a benzyl carbocation or a tertiary. Now we all have learned to like tertiary carbocations. But right now we're going to learn to like benzyl even better. We'll see in just a couple minutes. The benzyl carbocation is actually much, much more stable than a tertiary. The reason is the benzyl, being attached to the ring, is resonance stabilized. We'll draw some resonance forms in a second. So of these two, the most stable is going to be the benzyl carbocation. Now we'll do these resonance forms in a minute. Right now, this is our carbocation intermediate. Here, we're going to attack this with bromide, and we're going to form this compound with the bromine now attached to the benzyl position. If we did Markovnikov's rule on this compound, what would we have predicted? No, this has one hydrogen. That has none. Markovnikov would say the hydrogen would go here. He's wrong. So that's why Markovnikov's rule isn't always worth remembering. Simply remember, you're going to form the most stable carbocation. Benzyl is more stable than tertiary.
Would it be the same thing if it wasn't attached to a six-membered ring?
Nope, no, it has to be a benzene ring. That's why it's called benzyl. All right, go ahead and take these. Very quickly, just jot down the initially formed carbocation and the final product. On your second exam, you will have at least one and maybe several problems that have the same wordings that I just used. You will have a problem like this. You will be asked to draw the structure of the initially formed carbocation, just like you're doing now. And you'll have another box where you're asked to draw the structure of the final product. Well, the first one here, this is a primary carbon, this is a secondary carbon. We will form the secondary carbocation. The secondary carbocation will then add the bromine to give us 1 bromo, 1 methyl cyclohexane. And our second problem here, this is a primary carbon, this is a secondary, our intermediate will be the secondary carbocation. Chlorine will add to this carbon, and we will get 2-chloropropane. In our third one, we have a primary carbon and we have a benzyl carbon. Remember, benzyl is better It's even a line, sort of. Therefore, carbocation will form on the benzyl carbon, proton here, bromide will add. Here's our benzyl carbocation intermediate. And there is our final product. Yeah.
Sorry, could you explain like where you added each of the ions in the second one?
Here, we have, for our alkene, we have a primary carbon and a secondary, right? Secondary carbocation is more stable. Therefore, this is where the carbocation will form.
Meaning that
CO
that's where
minus will
the
attack
hydrogen is at?
at this carbon.
Hydrogen's adding to this CH2. Because of that double bond.
But that is the first step, right? And
Yep.
hydrogen.
All right, let's look at this guy. Once again, Markovnikov's rule does not apply here, does it? Because we have no hydrogens. The product of this is the 1-bromo, 1-chloro, 2-methyl cyclopentane. That's the product. That means, working backwards, that the carbocation formed here is more stable than the tertiary carbocation. Working backwards.
Why is it more stable?
Well, that's what we're going to do. This is what the carbocation looks like, right? And we have a positive carbon, and next to it we have this chlorine attached. Now remember, the Lewis dot structure, which I've shown here, chlorine has 3 pairs of unshared electrons. We can draw a resonance form where we take one of these electron pairs, move it in, and we form this resonance form. This is an example of a resonance stabilized carbocation. Just like I said, benzyl was more stable. Anything that can stabilize a carbocation by resonance is going to make it very, very stable. What sorts of things? Basically, any atom attached to the carbocation that has an unshared pair of electrons. Anything with an unshared pair of electrons. Once we have our carbocation here, remember bromide could attack from the top or from the bottom, right? If it attacked from the top, we would get this product where the bromine and the methyl were trans to each other. If we attack from the bottom, we would get this product where the bromine and the methyl are cis. Either coming in the top or coming in the bottom. Think about for a second, if you were this bromine coming in. It's not going to be an easy trip either way. But if you try to come in the bottom here, oops. Let's do the bottom one, this guy. If you came in the bottom, you would have to battle this methyl, wouldn't you? The methyl would be in the way. Methyl is big, bromine's big. Coming in the top, all you have to battle is the hydrogen. much, much less. Because of that, this is the major product. Stereochemistry here. Bromine and methyl, both the highest priority. This is E, stereochemistry. Here, bromine and methyl, highest priority. Same side, it would be C. This is the major product because this is the path of least resistance. Organic chemistry. Always go for the most stable intermediate and always take the path of least resistance.